Sweet. Oops. Oh, okay. That's what to do. Screen one. Yeah. So, do have it right here. Yeah, 7 o'clock. No. How's it going?
Oh, it's going well. How about you?
I don't know where my graduate assistants are, but outside of that, going pretty well. I have made you a co-host, so I'm assuming you have a slide. So
I am assuming I do too.
how's the family?
Oh, we're doing great. We're doing great. Hanging in there.
Excellent.
So not sure if I can use presenter mode or not. That's the only question.
Yeah, I think you can do it, but you have to tab shift or what is
Portion of screen. There it is.
it?
Okay, and then I will move over to,
Oh yeah, you're on a Mac.
yeah. So if I go this, I should be able to do that. Does that look okay?
Yeah, that looks good.
Perfect. How have you been doing?
Been doing pretty well. I just got to, well, not just, but I've been at George Mason for a year and a half now. Of course, I made the move right in the middle of lockdown, so that's fun. But yeah, outside of that, everything's been great. Primarily just teaching at this point, although I am slowly moving into Peter Plavchan's exoplanet group. So,
Oh, fun.
so yeah.
Didn't you work with Peter over a summer or something?
I did. I was part of the IPAC graduate fellowship, and yeah, I worked with him on YSOs. So it was just a happy coincidence that I ended up at the same institution that he was at. I'm starting to wonder whether or not I'm going to be doing the show.
Looks like there's more people in the waiting room. So
yes, those are all just guests. So yeah, I don't know how many people we're going to have tonight.
That's okay.
So yeah. So I'll mention this to everyone else, or to the people in there, but essentially we're going to have is I'll go through my slide, some introductory slides, and then I'll introduce you, and then you'll give your talk, and then after that someone normally a grad student would do this, but it's starting to look like I will be doing this. I will be doing a telescope tour, although at this point, I think the weather is crap, so we're going to do a closed dome tour, which you are.
All right, I can't send you my weather.
Well, it's still daylight where you are.
Not for long. Sunset's within the next hour.
All right. Okay.
Well, we don't have any remote facilities yet to where I could log in and do anything. So.
Okay. I thought, see, it's funny because I thought Embry-Riddle was in Florida of all places.
They have 2 residential campuses. This is a secondary one.
Oh, okay.
But it's been a growing, we were the first to have an astronomy degree program here. And then I joined a couple of years ago, and it's growing quite a bit. So we had someone retire due to COVID's just not wanting to come back in the office.
Understandable.
And, that's fine. The department's better now. And
one of those.
Yeah, we're hiring a new person to replace them
okay.
next year. So
sweet.
That'll be fun. And we'll have 3 full-time astronomers.
Yeah. Well, 3.
Yeah. And our physics program is largely like general relativity and LIGO. So it's really almost an astrophysics department, not a
nice. Yeah, I just came from LSU, so there's a large, obviously, LIGO contingent down there, and I have to say the LIGO people pretty much keep themselves. I don't know if that's it's a comment or if that's with all LIGO folks or just LSU LIGO folks.
It's not always true here.
Hmm.
I've been working with one of them because he's running the search for supernovae within LIGO.
Okay.
And how do you characterize if you detect a gravitational wave event from a core collapse? So,
Wondering, do they have the sensitivity to pick that up?
you can't go as far as you can with binary black holes.
Okay.
So, but my guess is we'll probably have one within 5 years.
All right. Sweet. All right. Looks like Kevin M, you're here.
Yep.
Excellent. Let me introduce you to Noel. Noel Richardson. He is a friend of mine. We went to grad school together.
That was a while ago.
That was a while ago. Yes.
Hello.
Kevin and Em are two graduate assistants attached to the to our local observatory. So,
how big a telescope do you have?
0.8 meter or 32 inch. So,
you actually have a bigger aperture than we have on campus.
What,
but I bet with weather, I can collect more photons.
Yeah, that's definitely true. How large is the telescope that you have?
We have a 16-inch, although we're about to get a 20-inch as well. So
nice.
20-inch will be a plane wave, which is much better than the Meade that we have right now for the 16.
Yeah, we have an optical guidance system, and I have to say that I'm not of plane wave, them and DFM. They're the third on my like. Plane wave makes an excellent telescope.
Yes, they do.
Were you still at GSU when they got the 24? Plane wave 24?
They were installing that, I think, as I was leaving. Like I didn't get to use that. I used the RC optics, and that was amazing. So
yeah. That was pretty good.
That manufacturer's out though, so.
All right, we will be getting started in the next couple of minutes. So let me share well, actually I won't share my screen yet.
How is the weather looking?
Cruddy, or at least it was about a half hour ago.
Yeah, still cloudy.
We have like 3 little clouds in the sky.
When is the monsoon season in Arizona?
Usually it starts somewhere around July 1st, although it's technically June 15th. And it goes until here it usually peters out by about September 1st. Okay. Somewhere around Labor Day, it's gone. We had a really heavy one this year. Everything got really green and lush, and it was within the top 5 recorded monsoon seasons everywhere that has more than 50 years of data. So,
hey, climate change.
Well, it's been really hot and dry for most of them, and I will say that the monsoon season over the summer is much better.
All right. Well, I'm going to start letting folks in.
Excellent. I'll shut up.
That's all right. Where am I? There I am. All right, this will work. All right, howdy, folks. My name is Dr. Rob Parks, and welcome to Evening Under the Stars. This is the last Evening Under the Stars that we will be hosting in this semester. We will be taking the winter break off, as I'm sure all of you will be as well, and we will be coming back in the spring. So before I introduce our guest, let me share. Oops, let's do this. All right. Yes, Derek, it is I, Dr. Parks. So Hopefully you can see my screen. Like I said, welcome to Evening Under the Stars at George Mason University. This is, or George Mason University Observatory. This is one of the lovely pictures that we have of it in the nice fall weather. This, as I've said, is the last one of these that we're going to be doing this semester, and we will be starting back up in the spring. Our telescope is located on a silver tower right next to Research Hall, and our control room nominally is right next door to it. I say nominally in the sense that because the one sort of silver lining of lockdown, we accelerated our project to allow us to do remote observing. And so we now have the capacity to observe really anywhere that we'd like, anywhere that has a solid internet connection. I'm actually logged in to the system right now from my office, which is actually a little bit below where that picture shows. The other thing that you can see on this slide are the various pictures that undergraduates here at George Mason have taken using our 32-inch telescope, ranging from stellar nurseries like the Orion Nebula to galaxies to planetary nebulae. All of a span of beautiful astronomical images, all of which have been, as I said, taken by undergraduates here over the years. We've really started we have a few grad school students here, Owen Alfaro being one of them, who is really starting to take to astrophotography and making great strides with it. Starting in the spring, we are moving from the Thursday nights to Tuesday nights. The exact time is to be announced, and the exact dates are also TBA. But we will be moving to Tuesdays starting in the spring. The way that our format is set up is that we invite guests from now all over the country, potentially even internationally if we can get so lucky. And they will provide us with a public talk lasting somewhere between 30 to 45 minutes. And then we will supply a 30-minute guided tour of the telescope. Assuming that the night is clear, we will open up the telescope and we will show you digital images that we can take using our CCD camera. And if not, as unfortunately I believe tonight is one of those nights, we will be doing a closed dome tour that our observatory GTAs or graduate students will be providing. And they will just simply talk about the telescope and provide you more images that have been taken here and talk a little bit about the research and the outreach that we do at the university or at this observatory. Speaking of learning about the observatory, if you'd like to learn more about us, what we do, who we are, that sort of thing, we put out a monthly newsletter. Again, we will be taking a slight break over winter, but starting up in January, we will be returning to our monthly format of the Moon, or the Mason Observatory Outreach newsletter, where like I said, we highlight the students that were working with us, the public nights that are available not only here, but over Northern Virginia, as hosted by NOVAC, the Northern Virginia Astronomy Club. And I do a bit about science news or space news, just talking about some of the more recent events that have happened in space, both from a manned mission perspective to just astronomical events. If you really like what you see here and would like to support us in not only in our research, but also in our teaching and more specifically our outreach endeavors, please consider becoming a patron of the observatory. We are, Dr. Peter Plavchan, our director, and myself are ramping up particularly our outreach arm of the department. We are now hosting a great deal of private tours, which include Girl Scouts, Boy Scouts, and we hope to be able to even travel to high schools or institutions that normally would not have the resources to be able to see the night sky or visit a planetarium or anything of that nature. So any sort of help financially that we could get, it would be appreciated. If not, we really appreciate just simply you coming by, participating with these events, just watching them on Zoom, or once we get over this whole lockdown business, coming by and actually looking at the observatory in person. And you can support us at various levels, depending on your interest in finances, all the way from going from star all the way to Big Bang, where you in fact will be a lifetime member and we will love you forever. We love everybody, but we'll love you more than everybody forever, if you go that route. So just this is not a one-person operation. Like I said, my name is Dr. Rob Parks. I am the deputy director of this observatory. Dr. Peter Plavchan is the director. He will more than likely be lurking within the coming by later on to observe. And the two people that you will be seeing after our guest speaks is Kevin Collins and M. Thunyapong. They are the observatory graduate TAs. And without them, we really would not be able to do the things that we do, particularly in terms of events such as this. They are really the work people behind the scenes. And we also have Jonathan, who is our president of the Friends of the Observatory student organization. So if there are any students watching, and I'm probably certain that a few of them are my students, if you're really interested in astronomy and you want to make sort of a social connection with others who love astronomy, please Google photo Friends of the Student or Friends of the Observatory student organization, and feel free to join. It's free to join. And we do, they host meetings pretty much bi-weekly, and there are also private or just photo only nights that they get to use the telescope. You know what? I don't think that I'm recording this. Oh, I am recording this. We actually automated that. Anyway, without further ado, I'd like to introduce Dr. Noel Richardson. He's a friend of mine from graduate school. He graduated a little bit before me and at Georgia State University, and is now an assistant professor at Embry-Riddle Aeronautical University in Prescott, Arizona. The specialty is massive stars and binaries, or essentially two stars that are orbiting around a common center. And when I talk about massive stars, what we're really talking about are stars that are 20, 40, 50 times the mass of the sun or more. These are ginormous objects, and they are very, very fascinating. And so he works with studying those and their evolution. He's doing a multi-wavelength study with his undergraduates, looking at, he'll be talking today about his observations of these objects from, I believe, infrared all the way to X-ray. But why hear this from me when you can hear it directly from Dr. Richardson himself? So, howdy, Noel. No, I believe you might be muted.
Well, you muted me earlier, so you know that happened.
All
right, so today I do want to thank Dr. Parks for inviting me. Rob and I have known each other for a long, long time, and a long time ago we observed together on a lot of small telescopes that were at our graduate school, and also used a infrared array of telescopes out in California that I'll briefly mention later. So as Rob mentioned, I study massive binaries. And so that does mean that there's two stars going around each other. It turns out that most massive stars, probably all of them when they're born, are born in double or triple or quadruple systems. There's almost no single stars that are really massive that are shown. And the reason for that is that when you bring these big objects together and you are trying to collapse a cloud, they start spinning a lot, and that that amount of spin, you can't put it all into one object, it'll spin itself apart. And so to have really massive stars, they usually need to have a friend nearby in order to have all that angular momentum. So I like studying these massive stars. They live fast, die hard, they explode as supernovae at the end of their lives. And I want to understand the evolution from how do they form to how do they die? And especially, what are those end stages like for these stars? So ever since I started here at Embry-Riddle, I have taken on a fair number of undergraduate students along the way. And so this is my current group. I have 2 of them graduating this term. I've had 3 already graduate. I've only been here about 2.5 years. So you'd think, okay, that leaves you with only 8 more, but I'm taking on at least 2 more next term. So it's a growing, expanding group. It's a massive research group on massive stars. So I am really enjoying these students. They are doing fantastic work. Okay, so what is a massive star? Well, if you look at a galaxy that's far away and you look at it with a really good telescope, you're going to find that you can see individual points of light in it. Or maybe you see these red regions. The red regions are usually what are called, it's glowing hydrogen that's lit up by very, very hot stars that are nearby. And so when you look at a galaxy, you see all these really massive stars. You don't see the stars like our sun when you look at other galaxies. You only see the really big ones. And so if I were to plot this on what's called an HR diagram, where I plot temperature or spectral type, temperature increases to the left, the brightness, the intrinsic brightness of a star increases going up, or the luminosity, then you would find most stars follow along this thing here that's called the main sequence. If we were looking only really close to the sun, we'd really only see this bottom part of it. But because we're looking really far away, we can see way up to the top and how big can stars get. And when you get up to this really high part where you're like 1,000,000 times more luminous than our own star, the sun, you get into some really interesting objects. And that's where I really think that it gets fun. Now, modern day astronomy, if we're looking at observations, there's kind of 2 ways you can go. You can say, I'm going to observe 1,000,000 objects and I'm going to understand statistically what's going on with any of them, with certain classes of objects. And there's also the so that's astrostatistics, but there's also astrophysics, where I delve deep into the observations and understand an object in depth in order to understand exactly what's going on. And so that might tell you something about how different objects are going. If I look at a supernova, if I want to know how many supernovae there are, that's going to take statistics. If I want to understand exactly how a particular supernova worked, that's more of the astrophysics. And so with massive stars, what I feel has been the biggest success of astrostatistics is in understanding binaries. And so if I were to just look at the models of how these stars work, if I have a binary that's formed with a certain separation, say up to about 10 times the distance of our sun and Earth, those 2 stars, if they're massive stars and the main star has like 20 solar masses or more, they're going to interact. They're going to basically swap material back and forth or something along their lifetime. Beyond that, they're going to act like we would normally teach a star would act in our introductory astronomy class. And what's really cool is that if you want to get at what all of these different systems are and you want to understand what's going on, for a random star that's about 2,000 parsecs away, which is relatively nearby for massive stars, you can probe any of these objects that are going to interact with modern observational techniques. Almost anything you can observe with a small telescope, whether it be the brightness of a star and how it varies, how the stars move based on their spectrum and seeing Doppler shifts, or even resolving the stars with interferometry, likely those stars are going to or did interact in the past. Whereas if you do imaging or some, even a high resolution imaging, most of those stars are going to be your normal textbook normal stars. And when you actually do the statistics of how the binaries are out there, what you find is that a very large majority actually interact during their life. Only about 30% or so are these, normal single stars that we would teach their evolution in a intro astronomy course and be done. And all the rest are doing something where they're going to impact their companion by the time they die. And so here at Embry-Riddle in Prescott, I like to say that we concentrate on the astrophysics and studying the individual weirdos in order to understand how they interact so that we can inform these statistical studies about what's going on in the big picture. So for example, you might have an eclipsing binary, and this is where the brightness changes because the two stars are going around each other. Well, there's a satellite out there that's looking for planets. That's great if you want to look for planets. And it's sampling the whole sky. It's called TESS. And there are just hundreds of objects out there where we can now look at these. And by looking at the way that these light curves, which is a change of the light with time, go with time, you can actually measure the radii and the masses of stars because you get the geometry of the orbit. And so we often will measure spectra. This is a spectrum of the sun. And so you get these absorption lines. That's for a normal star. You get these absorption lines, and you can measure how they shift back and forth one way or the other. We can do this for eclipsing binaries. I actually do this as a class project every year. Now, my observational techniques course, we have a small telescope on campus. It's even smaller than the one you guys have at George Mason. And we go out, we measure the spectra, we can see stars moving back and forth with time. And then we come up with nice models for the eclipses based on this data from the TESS satellite and radial velocities from our observations we make here on campus. And from that, my students are measuring masses and radii of stars and informing models of what's going on. Now, that's great. That's what my students do when they're first introduced to research, and then they get into the really, really cool stuff after that. So I'm going to focus a lot on what my students are doing beyond that. So, for instance, I have my student named Clarissa is working with me. She's working on what's called a BE star. Now, BE stars are these stars that have a disk around them. They're rapidly rotating and they're ejecting this disk out. And in this case, we found this high mass, what's called an X-ray binary that we think is one of these BE stars plus a neutron star. And it might even be what's called a magnetar, which is just a very magnetic neutron star. And Clarissa has measured an orbit for this object. And what was really interesting that we didn't expect is that it's circular. Normally, these things are very eccentric because to get a neutron star, you have to have a supernova explosion. You get some sort of asymmetry in that explosion. It gives it a kick, and you end up with an eccentric orbit in the long term. Well, what's really, really neat, and you can look at how these stars have bounced around in the HR diagram with their temperature and luminosity, but more interestingly, here is, the time or their age versus their masses. So we start off with a 12 solar mass star, and eventually it starts to dump matter on its companion. The companion spins up, gets to be more massive than it. The main star goes down to maybe about 5 solar masses. The companion's up to 15 or 16. These are the only two models that work for this particular system. And then it settles down for a little bit, and then it starts to dump more material again. And the main star that started off is down to about 2-ish solar masses of material. So that's not very massive. And then it runs out of fuel. And so normally that would be when you would get a supernova, but there's not very much material left, so it didn't lose anything, and you don't end up with a supernova. And so as a result, the companion is there in a circular orbit now, and that's the only way you can get a circular orbit. So Clarissa's really done some great work along the way, and I'm really impressed at some of the stuff she's done. Just as a generic thought here, like before in the first merger or the first, in future interactions, what's going to happen is the star will swell up. It'll dump stuff on there. I couldn't find a good one for this type of star right now. But this is a really interesting system. And that's probably the most normal of all the stars in my group, as far as what we look at, because we concentrate on what are called Wolf-Rayet stars and luminous blue variables, or LBVs. And so if we have our main sequence, the luminous blue variables are basically some of your most luminous, hottest supergiant stars that you have on the HR diagram. The Wolf-Rayet stars actually aren't even on this diagram because they would be off to the left, because they're even hotter than O stars, because we've exposed down to the deep core that's left over from it. And that's what a lot of them are working on nowadays. And so in the title, I said that there was colliding winds. And so what can happen is if you have two of these massive stars, they both get a wind, the winds end up interacting with each other and forming a shock between them. And so the best way to show this, I think, is a video that my colleague made. This is Gamma Vel. It has a Wolf-Rayet star. Big, huge mass loss coming off of it. O star with a little bit less coming out of it. And as the two shocks or two winds hit each other, you form a shock around it. And then they're going to run around and they're going to go around in their orbit. In this particular system, it's the closest Wolf-Rayet star to us. And it has an orbit of about 70 some days. And we can observe this with different telescopes, whether it be from the ground, with optical, or with X-rays, with telescopes like XMM. And our simulations tell us something about the conditions of the gas. How hot is it? What's the density where it's hot? And you can actually get X-rays out of it. Well, we've done this for several of our binaries now. And so I love Gamma Vel because I think it's a really close, nearby, interesting one. But WR140 is maybe a little bit closer and nearer dear to my heart. It is a really cool system that we've managed to work with a telescope called Chara, which I'll show you a little bit more about in a bit. And this is what the stars, how they look going around each other in the sky. Now, the units on this of how far apart these two stars are on the sky are what are called milliarc seconds. And Rob will tell you a milliarc second is a very small angle. And so a milliarc second is usually, I like to describe it as if, someone's out on the lake, 100 miles away from you reading the New York Times. You can actually, if you have a telescope able to resolve stuff at milliarc seconds, you could read the headline over their shoulder on that New York Times easily if you have that resolution. So WR140, we've managed to actually get masses that are within 1% or 2. This is actually a accepted paper now that's in there. And what's really neat is that it also, because you have all this shocked gas, you produce X-rays, and the X-rays have a certain way of behaving. And that's here in either the blue or the black, depending on what energy X-rays you're looking at. And as the X-rays go into there, what we actually find is that it switches between X-ray cooling of the gas by sending off more and more X-rays as the two stars get closest, to actually cooling via optical emission lines. And that was a new discovery that we only realized about a year ago or so. And what's really cool is when that happens and you switch the way of cooling that gas and the system is set up just the right way, a Wolf-Rayet star doesn't have any hydrogen left. WR140 in particular is mostly carbon and a little bit of helium coming off of it. It mixes with the hydrogen around it and you actually create dust. Like, this is a really, really weird thing. One would think that if you have a star with a temperature of 50,000 degrees, there's no way to get dust around it. And here we have these forming all the time. And so you get these really cool light curves where it basically, as the stars get closest together, the cooled off shocks further out start to produce dust. And we think this might be the first way that we ever made dust in the universe. It's such an interesting problem that WR140 will be one of the first targets with James Webb that I'm part of a team that's working on as it launches, in a couple weeks, which is really exciting. So I have another student that's worked on WR140. She's understanding how dust clumps in the line of sight may work using photometry. I have another student who is working on actually a similar system with an almost identical spectrum and spectral types. And instead of an orbit of 8 years like WR140, it has an orbit of 28 years. And she's managing to put a first orbit together. And we actually are looking at the infrared evolution of a dust cloud. And Andrea, like if we look at the data that we have, this is kind of a comparison of the last cycle and now. Some of our data, we've gotten more along the way. And then here's this infrared peak due to the dust. Now, Andrea is now working with data taken with SOFIA, which is an aircraft that has a 2.5 meter telescope in the back. And you go up above the clouds and above all the water vapor in the atmosphere to observe things in the infrared as you go further out in the universe. And so this is kind of a first look at the data. We're not done with it by any means yet, but we finally are getting it reduced and working on it. And these stars are so interesting. There's so many of these dusty Wolf-Rayet stars that we kind of want to understand how the dust forms, because we know that these ones are forming because of binary interactions between between these two stars and the way that the winds collide, but not all of them are confirmed binary. So I have another student who is actually working with doing a survey with Gemini South on like 40 of these objects, all of them that we know that aren't in the galactic center, and doing infrared spectroscopy at high resolution to determine if all of them are actually binaries. And along the way, I'm taking a couple of these cases and I'm trying to go more in depth. I'm using what's called the char array, and we're actually able to resolve them out like I did with WR140. And so one of the first students I graduated when she got here worked with me on this one. This is a nitrogen-rich Wolf-Rayet star. It doesn't form dust, but it had a nice orbit that we determined relatively well in spectroscopy and pretty darn well with interferometry, where we can get down into a orbit that is only about 3/4 of a milliarc second across on average, which I think might be the tightest orbit that's ever been resolved. And just for Rob's interest here, this tells you the size of our errors are so small that we can really pinpoint what's going on with this orbit. And while I'm still talking about Wolf-Rayet stars, and because I love promoting my students, this is Krister. He's going to graduate this year. He's working on another one, which is in the middle of this nebula that was recently featured on the Astronomy Picture of the Day. And there's a hypothesis out there that it might be a binary. And I think Krister has finally proven that it's just structures in the wind and not a binary. But it has this big ejection nebula around it, and it's actually moving through the sky really fast. So it probably used to be a binary, and now it's not anymore. A supernova explosion probably kicked it out of the galactic plane. Now, my personal favorite object in the sky is the best studied colliding wind binary, but maybe the least understood. It's Eta Carina. Dr. Parks would tell you that I've been talking about this thing ever since grad school and working on it ever since then. And we're a lot further along than I was at that point in understanding what this star is doing. We know that there's a period, it's about 5.5 years, and we think the eccentricity of the binary is around 0.9. This is what's called a luminous blue variable for the main star. Luminous blue variable just means it's a luminous blue and variable star. It's kind of a supergiant that's extreme. It has the highest measured mass loss rate for the primary star of about 10 to the minus 3 solar masses a year, which makes no sense to anyone. So that's about an Earth mass a day, just for numbers. Eta Car had its claim to fame happen in 1837 when John Herschel was observing in South Africa and found that the star was suddenly bright and rivaling Sirius in the night sky. It was the second brightest star in the night sky for a long time at that point. And it erupted. And at that point, it made this big nebula that's going around it. And so John Herschel was down there in Cape Town observing this. If you were really interested, you could even see his logs are recorded for posterity. The nebula itself has been well documented over the years. You could take spectra around it. They did this with the VLT, the Very Large Telescope, a while back. And then you can make these data cubes and understand how the gas is moving and create from that a model of what the shape of this cloud is. I have one sitting on my bookshelf in front of me. And so at the very center of all this, there's a binary star. And the binary star, I like to show it this way and just kind of introduce little bits of it along the way. So the primary star, or Eta Caurae, it's probably about 90 solar masses. It's some sort of luminous blue variable, has a huge radius, big mass loss rate, whereas the secondary we don't know much about. It's maybe a third as massive. It has a mass loss rate about 100th as much. And we know that the orbit is about 5.25 years. And every time they get close, there's what's called a Periastron Passage, when the two stars are closest. That creates an excess in the helium-2 emission line. There's a lower energy overall in the optical spectrum as the two stars get closer and the geometry in our line of sight. At the same time, the X-rays are highly variable. And there was a recent event in February 2020. We were getting all of our observations going, and then COVID hit. So I guess I need to go back to the telescope in a couple of years for the next one. We can actually zoom in on it. This is to scale, like if that's an arc second on the sky, which is usually about the size a star would appear when you look through an eyepiece. So you would see a cloud around it, kind of shaped funky. But if you zoom in with interferometry, you can actually look at the winds and put together a structure of how that colliding wind geometry and the way that the two stars are working against each other with their winds in the sky. These models have been done for many, many years. You can actually 3D print them if you were so inclined, which is really kind of cool. When my friend and colleague did this back in 2015, he actually managed to get one printed in sandstone that was done where the color of the stone at the different points represents the temperature of the gas, which is, I think, just really, really cool. Before I tell you everything our students are working on, I do want to do a quick side note of saying, here's a binary called Iota Ori. It's a highly eccentric binary, maybe about 0.7 or so, and it has a period of about a month. It's one of the brighter stars in Orion. I think it's in Orion's sword. And every month or so, it has a slight change in brightness that happens near its Periastron Passage. And we can model all this with programs. We can figure out exactly what's going on. We see little residuals in the light curve, which we see these little bumps and wiggles going on there. And those bumps and wiggles we can model and understand as pulsations for the star. And that tells us something about what's going on. Now, these stars aren't supposed to have pulsations. They're too hot. They're too big or whatever. And what's really cool is that because it has pulsations, we know that these are driven by it being in an eccentric binary. And so Eta Carina, I had a student working with me on a second project with this when I started here. She's now at University of Michigan doing her graduate work. We found pulsations that we could actually explain from this same idea of tidal forces driving these pulsations every orbit. So I thought that was really cool. And so Nora's did some great work on that, but we still have more to do before we can positively identify it as pulsations. Every time these two stars get closest, we see an increase in this line here, which is a helium-2 line. That means that it's helium that is so hot that it's acting like a hydrogen atom and only has one electron instead of two. And we can model that based on these same things that can predict the X-rays to understand what's going on with the helium-2 near the Periastron passages. Also in the optical, we have helium-1 lines. This is a spectrum, and the spectrum changes with time. So the dark parts are absorption, and you see it going through and the absorption changing with time. This was during our 2014 Periastron passage. We were able to understand some of that in this idea of what's going on with these colliding winds and the geometry there. So here we see these kind of fingers that point in from, if we were looking in from over here, which is roughly the right direction. And those fingers correspond to differences in density, maybe velocity, and in temperature of the gas, which we can then compare. And so now those wind collisions that we see in helium that were documented for the first time really in the 2014 event, my student Alexis is working on comparing 3 different events now in detail of what we can actually understand about these wind collisions in the helium profiles. My student Connor, who's about to graduate, he's working on changes in the observed ejecta. And so there was this line here. This was from the second eruption that happened in the 1890s. It's going away. And Connor and I have come up with a way of explaining why that's going away and why the system looks brighter than it did in the past. And it all is connected. And along the way, he discovered these new interstellar features that we kind of can agree that, you know, this one looks a little bit like that, but at a different velocity, or like the one here. And these are all related to what we actually see in these neighboring stars around Eta Carinae. And perhaps most excitingly, although I didn't put the most current picture on this, is my student Emily has finally measured an orbit for this thing, which has been the biggest problem for I don't know how many years. It was first thought to be a binary in the 90s. We haven't had an orbit until now. So that's really, really great. And I know I'm probably coming up on my limit of time. So I'll just quickly say, Ashley, who recently graduated, she's now down at Louisiana State, worked with me on LBV called P Cygni, understanding its variability and documenting 5 years of variations and modeling what the Fourier transform really means. And we could interpret that as one of the driving forces of these objects. So she did this for one. So now I have 2 students that are going to look at the entire population and the Magellanic Clouds, satellite galaxies of our own, in order to really understand what drives these things. And maybe the question I went to ask when I was a grad student of how do these things work, maybe I'll actually get an answer by the time I retire. So with my final thoughts, I have amazing students. I've tried to highlight them along the way. But I think that the combination of high quality observations along the way with theoretical simulations tells us a great deal about physics of what's making these systems run. And that, you know, these weirdo stars may be closer to what we expect for other massive stars. And that I'm really excited about how we're getting masses for Wolf-Rayet stars, because that's going to tell us how mass transfer happens in these systems in the future. And with that, I just want to say thank you again for inviting me to give a talk. Hopefully I didn't go too much over, and I'll answer any questions that may be there.
Thank you, Noel. Appreciate that. If we could have a round of virtual applause from folks, that would be awesome. Thank you very much. So yes, if you have any questions for Dr. Richardson, please put them in the chat, and I will be happy to ask him for you. But I'm going to take the host prerogative and ask the first question, which is, and perhaps a very naive question, but what is exactly the Roche geometry of these massive close binaries that you're looking at? Because they have the shock winds, but essentially, I guess my
shock winds they're probably not quite filling a Roche lobe.
Okay.
Because they're probably not transferring mass anymore. They probably turned off the mass transfer, and it gets really interesting because when you have a massive binary and one of them starts dumping material on the second one, that's going to cause the orbit to shrink until the 2 stars are equal mass. And then if it continues to throw matter that way, then the orbit starts to get bigger again. And at some point you get big enough that you can turn off that mass transfer. And at that point, if you have two stars with winds, then they can build up that shock in between. You get these colliding winds that happen. And then you can do things like create these dust clouds around the Wolf-Rayet stars or whatever. And some of them are circular, some of them are elliptical. You can actually end up with kind of getting a extra momentum kick when you have a very high mass loss rate, where you basically can build up the eccentricity. So you start off, and if you transfer mass at the closest approach, then that can give you a little extra kick, so that the next time you'll give it a more kick and get more and more eccentric with time, which could be one way to build up these highly eccentric systems like WR140. Adacar was probably a different scenario, and I'll just leave it at that.
I was going to say, I would be very disappointed if you hadn't brought up Adacar.
I'm glad I could spend half the talk on
it. I'm also curious about the dust that you were talking about. I would not have expected dust in these systems by any means. Where is the dust forming? Is it circumbinary, or is it, where do we actually see this stuff?
I wish I had a better image for that with me in this talk. So if I go back to the first geometry of the orbit, so you get this collision here, and then when material goes in there, it kind of flows down that shock. And when it gets far enough out, it's cooler, and you can start to condense the molecules. So in a case where you maybe have a Wolf-Rayet star, carbon-rich Wolf-Rayet, you get carbon-rich material from that in the shock cone, and maybe hydrogen-rich material from an O star. And when the two mix, then you get those hydrocarbons, and you might be able to start building up the small rings or whatever in order to build up your dust with time. It's a very complicated question. No one's fully solved it. I am happy to say that, the geometry does look to be in shock cones. There's some geometric models we can make that explain observations at this point, but that's about as far as we've really gotten at this point.
Okay. Oh, very cool. Kevin asks, are there any interesting questions that are very difficult to answer with current telescope resources that might be easier to answer with the upcoming JWST?
So, as I pointed out, we are observing WR140 and another one which is similar, WR137, with JWST shortly after launch. It's an early release science project, so it should be next summer we're getting these observations. And with these observations in hand, what I can tell you is that when we observe the stars with things like Sophia, we get an integrated source. All the dust and star are all in one pixel, and you're observing everything, and you're trying to make the most of it and deconvolve what's going on. With James Webb being out in space, we're going to be able to actually take a look at this dust cloud and get spectra of just the dust that doesn't include the source. And so with that, we'll be actually able to say, this is what the dust is composed of. This is where we can really understand it. Also, along the same lines, telescopes like Hubble are very important for understanding some of this, because Hubble allows us to look at the ultraviolet. And in the ultraviolet, both of these stars tend to have a pretty strong wind. And so, for instance, here's some models for WR137. And in the UV, you can get these spectra down at, 1,500 angstroms or 150 nanometers. You can't start seeing anything in the optical until about 3,000 or 3,500 even. And that tells you something about the way that these wind lines play into effect. And both stars will have their own wind lines. And when you combine the two, you can actually model what each of the component stars are doing, and in order to understand what that mixing must look like out there to create the dust. So I think that there's a lot to do with a lot of different telescopes along the way.
Fantastic. So I am very impressed with the size of your research group. We have with Dr. Dr. Peter Plafchen, he works with both graduates and undergraduates, and I have to say that you have an impressive array of different students that are working for you. We have I suspect that we have a number of we have a number of undergraduates in the audience, and I was wondering if you had, given your experience working with these students, if you had any advice for students who are looking for careers in not only just astronomy, but science in general. What would you recommend they do now to help them better prepare for their careers?
What I typically tell all my students is that I want them to be marketable for whatever they choose to do. Our curriculum here, we teach like many other places. We teach our students to be prepared for graduate school in physics and astronomy. And I think that most physics programs are the same. We don't necessarily teach to get them involved in industry along the way. So they need to have skills that are transferable for either if they're going to be successful in their careers. And right now, if I were to tell any student what do they need to learn in order to be successful in their career, I tell them to learn Python and to learn how to code with it and learn how to solve problems with it. Because for a physics or astronomy major, learning Python is a way that they can then sell themselves as someone that can solve amazing problems with the current state of the art as far as programming goes. And that has allowed some of my students to do quite well. So I strongly suspect Emily here will have a nice job in industry. Although I will say that most of the rest of them want to go to grad school right now. So we'll see how the dice falls for them in the coming year. But I try to get my students involved really early. And by the time they're graduating, most of them are coming up with first author papers now. So I'm really impressed at their skills. And it starts, they take my observing class where they use a telescope and learn some programming in Python for astronomy in their sophomore year, so that by the time they're a senior, they are able to produce really great research, and they are doing phenomenal work. Several of them have been involved in telescope proposals or in peer-reviewed papers. So I'm really excited to see where it all goes in the future and where our program goes. And I hope that other programs start to take up a similar approach. When I teach them at our telescope and I teach them about binary stars, yes, they're learning how to use the telescope, but they're learning all the data analysis tools. And I end the semester with them briefly using the state-of-the-art software for eclipsing binaries called The Physics of Eclipsing Binaries, or PHEBE. That was written by Andre Persia up at Villanova. And this is a great software suite, and the students are getting their brief introduction into it. And at least one of the students will be using that for her senior thesis as well, so that she'll have had that fundamentals taught to her in class, and then move it forward from there into a better research career as she moves forward.
Okay, awesome. Yeah, actually, I have a question about what you're showing right now. But we do have a person that in the audience who is curious about much younger students. Where would you recommend, say, elementary or high school students? Where would you suggest they begin their astronomy journey?
Get a pair of binoculars and a planisphere, and be able to go out and point it with your own hands to know where you're pointing based on looking at the map, and look at the sky. I often say telescopes are too hard when you're first starting out, that the binoculars are really the way to go. But that subscription to a magazine like Sky and Telescope or Astronomy will go a long way in just teaching you some of the basics. And those tend to be more up to date than any books that you get at the library, because astronomy is a very, very fast evolving, changing field compared to other sciences. So I always suggest that way. And even if you can't do the binoculars, just getting a planisphere or going to, getting a free one online, like at skymaps.com, you're able to actually go out and understand stars and where they are in the sky. And some stars that you can see with the naked eye are variable. And I think those are really great to catch your attention and see what's going on. There's a famous eclipsing binary called Algol that you could actually even track on your own. And I think that these are great ways to kind of learn the night sky and learn what's out there so that you could go on and become a scientist, whether that's an astronomer, biologist, or, someone that deals with data for banks. I think all of that, all of those require certain skills and certain inquiry that we can teach our students along the way.
I definitely agree with that. And I would also agree with if you are looking to get your children involved with astronomy, I would definitely recommend starting with a pair of binoculars. So a lot of the less expensive telescopes are really just very difficult to use and very difficult to work with. If you're using with binoculars, I would also just recommend getting a tripod to mount them to see whether or not to basically stabilize.
Yes.
But yes, starting out with a pair of binoculars and basically a planisphere that allows you to determine what stars in the night sky, depending on your location, the day, the time of year, that sort of thing. Yeah, I definitely would agree with that. And so the last question I will ask before we turn it over to Kevin and Em for the telescope tour is, what is the instrument that you were using? What is your spectrograph? I gotta know.
Currently installed, we have, it's actually, you can there's a fridge on its side, a wine fridge here in the observatory dome. And that's to keep it at a more constant temperature than I could have it just in the dome. And we have one of these off the shelf spectrographs. It's a Milliarc manufacturer. And Milliarc makes a moderate resolution, what's called an Echelle spectrograph. And so for anyone in the audience that wants to know, basically this is derived from the French word for ladder. And you have one high resolution grating, which is kind of like looking at stuff with rainbow glasses, and then a prism that will send the light a different way. So if you look at your rainbow glasses, you'll see that you have one spectrum here and then another one further out that's a little wider, another one that's even wider that's further out. And eventually they may start to overlap depending on how good your eyesight and how bright the source is that you're looking at. And you can imagine that goes all the way out and you have hundreds of these orders eventually, and they just get fainter. And it depends on where it's meant to be dispersed. And so the Echelle spectrographs are ones where the optical is optimal when you're out in like orders 30 to 40 or somewhere in there. And so you're in pretty high resolution mode, but you have one order here and then the next one's here. And so they would overlap. So the prism will take that and it makes a set of lines that look like a ladder on your chip. And you get the whole optical spectrum at once to where it'll look something like this, but not at quite this high resolution. And so we have one of these on our telescope. I found that we can reach about, with our 16-inch, we can get about to 8th magnitude or so in a half hour with our skies. So wow. With a signal to noise that's reasonable enough for velocities.
Nice.
Yeah.
Is it fiber fed?
It is fiber fed. So it comes off so in this case, it comes off the telescope up here. It comes down a fiber, and it goes kind of through the back and then into a hole I drilled in the side of the fridge and into the spectrograph from there. Nice. And that's how we get our data. And then we have two telescopes in there. One controls the spectrograph and the cameras, and one controls the telescope itself.
Fantastic.
And up until now, it's always been controlled from in the dome, although we are working to make this a little more remote in the future, in that we'll have a control room in the neighboring building. This one will never be fully automated because this dome, you actually have to push it manually around. in order to observe, which I have never encountered except for this one. But we have hopes of getting a second telescope installed that will be a lot more accessible from that standpoint.
Excellent. Yeah, Peter and I are constantly chatting about upgrades to our telescope, adding more instruments to it, and having a spectrograph would be phenomenal if we can do that. But at that point, I would like to, if everyone could, or if people could, give another round of applause for our excellent speaker. Thank you, Noel, for accepting this the invitation and
It was
providing with such a good talk. So we will be switching over to our telescope tour. Noel, if you'd like to hang around and see it, feel free. Or if you need to take off, feel free as well.
All right.
But
thank you very much.
You're welcome to stick around and see what our facility is like. Unfortunately, as I've mentioned before, for newcomers, we do not have good skies tonight, so we will be doing a closed dome tour where Em and Kevin will be discussing the telescope, its details, and then showing you canned images of objects we've observed in the past. So yeah, I don't know which one of you is going to take over, but Em or Kevin, take it away.
Yeah, let me just share my screen for the. There we go. Can you see the webcams here?
Yes.
Excellent. All right. Welcome everybody to GMU Observatory. Virtually, that is. Unfortunately, again, this is going to be a closed dome tour. As you can see in the bottom left image right here, we've got pretty bad cloud cover all around. But I do invite you to come back next semester when we hold more of these events so we can see things opened up, get a live view of whatever's up in the sky. And also maybe a little bit further in the future, we might start having these events in person again, and maybe we can get a live look through the eyepiece, which is always a lot of fun. So we're now looking at the roof of Research Hall, like the image that was shown at the beginning of tonight's talk. Down in the bottom left view, you can obviously see that the dome itself that protects the telescope from the elements. It's about 20 feet across or so. And just above that, you can see the main event, our 32-inch telescope. The 32-inch is the size of the primary mirror in the back of it that gathers all of the light from the sky. And this is a reflecting telescope. So the two primary types of telescope are reflector and refractor. And that is based on what kind of optics it uses. Refracting telescopes use glass lenses, whereas reflecting telescopes use mirrors. Most big telescopes like ours and the Hubble and things like that use reflecting telescopes because mirrors are both lighter and cheaper. The particular optical design of this telescope is called a Ritchie-Chrétien Cassegrain reflector. And it's a pretty popular optical design for large telescopes like this. And essentially, as the light travels through the telescope, it bounces off the big mirror in the back, the primary, and then gets reflected back up the tube to a secondary mirror about a foot across before being reflected a second time through a hole in the primary mirror, which is shaped like a donut, before then being reflected one final time into one of the various instruments on the back of the telescope. Now, here in the top right, we have a view of our control room. We are controlling it remotely, so we don't have to actually be there in person anymore. I'm actually logged in to a computer that's just on the very left-hand side of the control room webcam, if you can see it. But before we had this set up, this is where our research observers would be spending a lot of their time. And then this bottom right view is one of the two motors we use to actually point the telescope. There's this one that twists the fork that the telescope set in, And then we have another one just like it here on the end of the fork that points the telescope basically up and down. And between those two axes, we can point the telescope pretty much anywhere in the sky. And we can control it using software. This is the primary software we use called the SkyX, and it's pretty much a point and click interface. You can see this outer green circle is indicative of the horizon. And so everything inside this circle is what's up in the sky currently. And this little yellow bullseye is where the telescope's pointed right now. And I'm actually going to take it and point it ideally towards the webcam. And as I move it, I will go back to the webcam so you guys can get a good look at it moving. And there we go. Ideally, I'll move it far enough that you can actually see the mirrors on the inside of the tube. Here you can see the secondary mirror popping into view, being held up by these support struts. It's again about a foot across for scale. No, it's just moving slowly, that's all. The footage is jumping a little bit. Okay, we need to move a little bit more this direction. All right, and now you can just see the edge of the primary mirror has come into view. Let me move a little bit further. There we go. And now you can see our nice, actually recently cleaned primary mirror on the back, as well as the hole in the middle, because it's donut shaped, where the light gets sent down into either the eyepiece or one of the various instruments that we use. Okay. Let's see. I was going to check some questions in the chat, but it looks like they have mostly been answered. Oh, how often do you clean the mirrors? It's actually quite an involved process. It's every several years, actually, because of all of the work that's involved. It's a very delicate procedure, too. Of course, you don't want to get any scratches or put anything on it that shouldn't be there to affect like its special coating or anything like that. So it's only every couple of years. That's also why it's very important to keep it inside the dome and to be closed up on nights where there's high humidity or chances of rain or anything that might actually hit the mirror. That's we want to avoid that if at all possible. And with that, I think for now, I'm going to park the telescope, put it back to where it was, and then I'm going to, once I see that that happens safely, turn it over to M, our other observatory TA, and he's going to tell us about a few objects and show us some pictures that were taken with the observatory telescope. In the meantime, I'll be in the chat answering any more questions you guys might have. M, I'll turn it over to you.
Okay. So oops. Let me take over from the application. Okay. Right, so looks like the telescope is parked. Now good to go back and check on SkyX. So the object I want to show you is about right above the horizon. It's actually below the orange line, which is 15. So the orange line is 15 degrees above the horizon. It's where we it's a limit we set up when we capture the object. We try not to go below this because it's bad for the telescope. This object is called Betelgeuse. It's in one of my favorite constellation, Orion. This is because it's a very bright object on the sky. You can see it. You can see it with your naked eye. I think I also have it on Stellarium. It's also a virtual night sky for the tour like this, closed dome tours. So this Betelgeuse, it's actually the 10th brightest star in the night sky. We can see it with our naked eye. Some astronomers use it along with a few stars to navigate the night sky. I think this is better. And we have some, let me close this application. We have some picture of this object. This object is taken when the cloud is partially blocked, but you can see that it's still it's still conspicuous through the cloud. It appears to be reddish because we classified it as red supergiant. Its spectrum type is about M1 or M2. You can see, although it appears as a dot, it's actually 800 to 1,000 times bigger than our sun, measuring by the radius. We call it red supergiant because of this, and this is a type when the star is at the end of its age. So this Betelgeuse is quite old. It's about some astronomers believe it's about to explode. Recently, that it can shrink and grow periodically because the radius, because when this, the main sequence star, or actually every star on the sky could burn out the fuel at the core, its own gravitational force make it shrink, and then its core is reheated and then it grow again. But this effect is more obvious when the star is at the very end of its age. Okay. So I think Betelgeuse is one of the good example of the evolution of stars. So now we are going to look at some nebula. So Betelgeuse is at the end of the age. We're now moving to the beginning of the star. This object is called Orion Nebula. It's still in the constellation of Nebula. Sometimes we call it Messier object 42. I can show you from the SkyX. So if we see this object on the sky, I think I cannot zoom it. I will just show you like this. So it's in the constellation of Orion, and it's appeared to be under what we call Orion belt. this, you can see the small word M42 here. This is where this object is located. This is taken by our telescope. It appears to have some bright parts, some dark parts, and another bright part. And as we zoom in, you can see some spots. Some are background stars, but some spots in this cloud is actually inside this region. Those are where the stars are formed. So Orion Nebula, the word nebula means cloud. It's a cloud of gas. Mainly, those gas is hydrogen atoms. So those hydrogen atoms are clustered together, and from physics or what you may know, the more massive object attracts more. So so when the gas is clustered, it creates a relatively more massive region on that on this nebula, and then this region attracts more mass, and those mass are accumulated until the core is crushed by the mass around, right? And it heats. And as the core is heated up to some point, it can start the thermonuclear reaction, and that's how the star is born. Okay. Actually, I think I may go back to Stellarium. There are several nebula in the constellation of the Orion. We have M8, M42, and then Betelgeuse. I think we also have, I think I may go back to the folder. Can show you Crab Nebulas. Those are image taken by our observatory telescope too. So Crab Nebula is similar to the Orion Nebula. It's the diffusive nebula where new stars produced. We can see it vaguely that there is some spots where the gas is clustered. And I think that's what I have for you. Kelvin, if you have anything to add, I'll pass it to you.
Mm-hmm. I would like to talk a little bit more about the Crab Nebula. I will say, as it's sort of thematic with what our previous talk was about, the Crab Nebula is actually the remnant of a supernova, which is what occurs when a massive star dies, essentially. So once a star runs out of fuel to do fusion, it no longer has that outward pressure keeping it stable and supported. And so a lot of the material of the star falls in on itself. And if it's massive enough, this will cause it to essentially implode into a huge supernova explosion. And this particular explosion, which the Crab Nebula is basically an ongoing explosion. This supernova explosion was actually observed by humans and recorded. So Chinese astronomers actually witnessed this supernova explosion occur in the year 1054 AD, so nearly 1,000 years ago now. They noticed a very, very bright object in the sky. At the time, it was about as bright as the moon and could actually be seen during the daytime. And it faded over the course of the next few weeks and months until it was no longer visible during the daytime or easily. But then multiple centuries later, Western astronomers actually found this object. And it wasn't until quite a bit later when they reconciled their observations with Eastern astronomers that they noted that this object had actually been found before, long before any of the Western astronomers were looking at it, because it was actually witnessed live in 1054 AD. So that's pretty cool that this event was actually witnessed sort of when it happened, although the Crab Nebula is about 6,500 light years away. So it took about 6,500 years for the light from the explosion to actually reach us. I also did want to mention, there were some questions in the chat. I forgot to bring this up when I was talking about the telescope, but the field of view of our camera that we use is approximately 26 arc minutes across. Each arc minute is about, well, each arc minute is 1/60th of a degree. So we're a little under a half of a degree across the sky. For reference, if we took an image of the moon, we would not be able to fit the entire moon inside of our camera at once. You could only see maybe 2/3 or slightly more of it in the image. I think that's probably a good question in the chat. Have we ever witnessed anything like that, like a supernova explosion, like the one from the Crab Nebula? I don't know of one in recent memory, but I also haven't kept track of such things. Dr. Parks, do you know of any more recent supernova explosions? I mean, I guess we have watched them occur at much larger distances that we've seen with telescopes and things. Has there been a similar, like, live view, you can see it with your naked eye type supernovas?
I believe the last one that occurred was in 1987, which was 1987A. That was seen in the night sky in the southern hemisphere. There have been supernovae since then, but nothing that would be dramatic to the point you would say, oh, look, that's something new.
Right.
Yeah, I think most supernovae we observe is just a tiny dot, right, from the distant galaxies.
Right. And I think we observe something like, I feel like it's something like 10 supernova per, I'm not going to give you a number that's wrong. So never mind. Another question, is it possible to see a black hole on here? Not directly, as black holes obviously don't emit their own light. The best we can really do is we can image galaxies that some of which have supermassive black holes at their center. It's surrounded by lots of very hot, bright material called an active galactic nucleus, or an AGN. So we can see kind of the effects that some black holes have on their surroundings, but we can't directly image a black hole. And even if we could, I guess, they would all be significantly too far away, I think, to really make out anything. Yeah, we don't have that kind of resolving power to see something pretty small and also not emitting its own light.
The recent image of black hole, I think that took about half of the Earth telescope to spot on, right? We cannot use just single telescope to look at the black hole directly.
Yeah, that was done in the radio, or more specifically the microwave region of the electromagnetic spectrum, and that used I want to say half a dozen to maybe 6 or 8, I can't remember the exact number, telescope or telescope arrays, which are fairly evenly spaced over the entire globe. So we were able to simulate the resolution of a telescope that is the size of the Earth. To give you an idea of what Dr. Richardson was talking about, milliarc seconds, that sort of resolution, this was even finer than that. So yeah, was able to simulate a really big telescope.
Yes, it is really hard to see a black hole. It was a gargantuan effort to get that popular image that exists. Yeah. Well, that's, here we go. We can actually, let me show one more image. This is the fireworks galaxy. It's called so because it actually has a significantly higher than normal rate of supernova. So they look like tiny little fireworks as they as the stars explode very, very far away from us. And this is a very nice recent image taken with multiple wavelengths using different filters through our telescope. Our raw images actually come out in black and white, but we can assign different wavelengths of light, different colors, and create a false color image, which is not just fake. It just might not necessarily look exactly the same as our eye would see. But you can, for example, take an image in a red filter and a green filter and a blue filter, and then stack them on top of each other. And it actually comes out in a process pretty similar to how you print regular pictures or like use film. Yeah, I think we'll probably end it off there. Thank you all so much for coming. And again, we'll invite you to next semester. We look forward to having many more of these different speakers, and hopefully we will be able to open up and actually get some live views next time. I guess other than that, we'll stick around for a few minutes, answer any lingering questions. The recording should be posted relatively soon, probably within the next week or two, I would say.
Sometimes we post it within 3 days, or sometimes it can be 5 days. So allow 3 to 5 days.
And yes, for those of you here in Dr. Park's course, I believe taking a screenshot is the signature for the event.
It is. It is.
All right.
Thank you, Em and Kevin. Excellent work as always. And for the rest of you, please have a good night and happy holidays. And as Kevin says, please consider stopping by next semester, and hopefully we will be able to show these things in public or in person. And also I'm hoping to be able to combine these events with our planetarium, our portable planetarium. So hopefully things will be much more exciting. Not that they're not exciting now, but we'll have much more things to offer you in terms of viewing the night sky next semester.
We will get to use this stellarium inside the dome. So instead of seeing this in the flat screen, you will see this stellarium surrounding you.
Yes, it is. It is pretty impressive, or at least it's one of the things I've got. I like. Oh, Zane, you have a question for me. maybe, possibly. That is to answer that question. So for those of you who are still here, if you are wondering where to turn in the assignment, there is a Google link that is, or a link to the Google Drive in my syllabus. So check that out, and you should be able to put it there. Please, when you do so, please create a folder with your name and select or place all relevant files within that folder. Thank you, Derek, for putting that up. Okay, I think that'll about do it. So again, thank you, Kevin and Em, for a wonderful telescope tour, as always. And yeah, I'm so long, peace out, and again, happy holidays.
Thank you.
Thank
Have a
you,
good
Professor.
break.
Mhm.